Because it didn't say like, that's a good example. But
okay, guys, welcome to our little revision session here. As I've said all along with you guys are all guinea pigs. And so what we're doing, because this is your first stage 6 exam, we're actually going to try and give you a bit of a almost adult stage 6 experience. What we're going to do is period 1, we're going to go through module 1 and 2. Period 2, we're going to go through module 3 and 4. Period 3, we're going to sort of do some practice on multiple choice. And then after lunch, we are going to look at answering extended choice questions or extended response questions. Okay, so feel free to ask any questions if you want. We're also going to recording this, and if you want to go over anything, it'll be up on Google Classroom after school. Okay, so of course, module 1, sorry, just gotta make sure we've got the right thing. Okay. Oh, no. Okay, Ms. Lee, Dr. Khan, you can see the presentation. Okay, guys, thank you. So, sorry guys, am I interrupting your conversation again? Okay. So, what we are doing here, we're going to go over the first couple of ones here. And if you remember all the way back to the start, what we're doing here is we're looking at the first point of any scientific idea, any scientific investigation, which is this idea that observation is really important. And it's this idea of when it says, how does it instigate a scientific investigation? We're essentially talking about how does science start? And there's plenty of examples. You can go back hundreds, thousands, tens of thousands of years where we have examples of scientific investigations happening. And so if we look here, what sort of observation do you see there? What's the observation? A candle is burning. And so this idea here is you make an observation and then you can go from there and you can start talking about different ideas and different things. You also have other examples here. What can you see in the middle of that picture there? What's a tiny little thing in there? No, it's not a plant. Next to the plant is a tiny little thing. It's basically a slater, also called pill bugs, anything like that. And can you remember back? We didn't do this as an investigation. We did do this as we observed some videos online. But how do insects react to things like light? What do most insects do when they see a light source? Well, not necessarily go away. Have you ever had a light on in the middle of summer when there's a lot of moths and things like that? In general, animals are attracted to light. Some are attracted to damp, some are attracted to a whole range of other things there as well. Another example. What is that diagram representing? What is that? Bernoulli effect. Okay, and essentially the Bernoulli effect, what we are looking at is difference in air pressure. And so if you look at the bottom there, wings are shaped that way. because on top, the air takes longer, or it has a longer distance to get through there. Effectively, what that does is decrease the air pressure on top. Air pressure moves from low pressure to high pressure. That is just an observation that people made. You can make that observation yourself by getting a piece of paper and blowing across the top of it. The paper actually goes up, okay, because of the air pressure differential. And what's our observation here? Rock strata. And what could you say comparing the rocks at the bottom to the rocks at the top? What's that? Yeah, in general, rocks at the bottom of layers are older than the ones at the top, okay? So those are just 4 very simple observations we made early on. Any questions about that? No, that's relatively straightforward. Other thing we need to do as we're going through this is think about the different types of data that are going on. Qualitative and quantitative. Really simple. Qualitative data is data you can't say is a number. Okay, so if we're looking at something there and we say it's not a number, then it's going to be a problem there. So people are wearing maroon jackets. That is not a number, it's just a statement. But it's a piece of data. Okay, it's got maroon, a color. We're not assigning anything to it. Quantitative data, of course, a quantity you express as a number. I could say, let's just say, what do we have, 25 people here. 20 people in this room are wearing maroon jackets. That is taking some qualitative data and turning it into quantitative data. Now, of course, can it be counted? Yes or no? That's pretty easy there. The data type, qualitative data. If you're looking at a picture, that is qualitative data. If you're looking at a graph, which has numbers on it, you're looking at quantitative data. Now, you've got other ones here. We don't need to go too much into this one here, because I think that first slide there sort of talked about a little bit there. But basically, in science, most of the time, we are looking at quantitative data. There are times that we look at qualitative data. An example of that would have been Diane Fossey, who did some research into primates. She couldn't do an experiment. She just looked at what they did and gathered data that way. We also have the idea of observation versus inference. Now, this is a really, really important thing because the difference between observations and inferences, I think you guys as a group kind of get it, but a lot of people wouldn't. Observation, something you directly observe yourself. Okay, so the example here, the plant is extremely wilted. Okay, poor plant sitting there, all dried up, not much going on there. The car has stopped running. Or going back, you guys are wearing maroon jackets. The inference is what you take from that. And so if the plant is extremely wilted, the plant is extremely wilted due to a lack of water. So in other words, what scientific process are we kind of implying there with our inference? Starting with H. Yeah, when you're doing an inference, you're applying a hypothesis to your observation. Car has stopped running, it's run out of gas, or you've turned it off. Okay, observation you directly observe, inference you don't directly observe. Okay, cause and effect. We have here 3 examples that we have talked about. Archimedes. Now, of course, I think everyone knows Archimedes with his taking his baths. What word is he accredited? What's an ancient Greek? What's that? No, what was that? Eureka. Okay, so Eureka is the word there. And basically we all know the story that Archimedes, I can't remember, does anyone remember the name of the king? What was that? Well, some Greek guy. So the king was being sort of screwed over a little bit by a crown maker, and Archimedes, by getting in the bath, noticed that there was displacement, and he was able to link displacement to density, knowing that gold is denser than silver, and that the crown maker was substituting some silver in there so that he could steal the gold. observation leading to inference, leading to cause and effect. So in this case here, the effect is that water is displaced because Archimedes' body has mass and volume. It has a density and it displays, or in this case here, volume is probably the more important bit. So, also, we have another one here, Alexander Fleming. And of course, we've talked about this a little bit here. Alexander Fleming, what did he observe? Go back a step. Not just he observed, he was working with penicillin, he was working with molds, he was working with petri dishes. And if you look at the screen there, you can see in terms of our modern microbiology labs, it's a bit ancient there. He's just got petri dishes piled up everywhere. In this case here, this was Fleming had another serendipitous moment, a little bit like Archimedes' Eureka. He had some petri dishes there. There was a bit of mold getting into one of them, and that mold destroyed the bacteria. That led to antibiotic treatments using penicillin. And of course, we then also have Galileo. And you guys tell me, what was Galileo doing? Okay. Observing Jupiter's moons. And what did Galileo disprove? Geocentric, yeah. So for 2,000 years, thereabouts, probably close to 1,500 years, most people assumed that the Earth was the center of everything. And that is your observation. Everything seems to move around the Earth. By Galileo's time, they sort of noticed things like the planets, which most of the time were called the wanderers because they didn't seem to follow the patterns of everyone else. They were a little bit different. And of course, Galileo's big observation leading to this new idea was he looked at Jupiter through a telescope. Now, Galileo didn't invent the telescope. He was just one of the earliest people to actually use it in a scientific way. Prior to that, it was basically a toy. People would use the telescope to basically look at other people close up. Galileo looked at Jupiter and saw that Jupiter appeared to have at least 4 moons going around it. That disproved that the Earth was the center of everything else. Okay, so he was able to link that quite probably the sun was the center, which led to the heliocentric model, and that the geocentric model really couldn't work as effectively as people thought. Another little thing here where we've done a fair amount on the indigenous observations. Fire stick farming. Now, we've talked about that a few times there. Essentially, what you're doing is taking an area and you're burning it. There's probably 2 main reasons we've talked about that we do the fire stick farming. Can someone quickly tell me? Can't remember this. Am I going too fast, too slow? Yeah. Australian trees. We've talked about this before. Australian trees are good portion of them are eucalyptus trees. Eucalypts need their seeds, and a lot of the other native seeds as well, require burning to actually start germinating. By the area being burnt, 1, it cracks open these seeds, but 2, it also provides a lot of fertilizer. If you've ever seen an area just after a bushfire, it has brand new growth very quickly. And that's because you've got seeds, you've got all the burnt material, which is broken down into its chemical components, is there ready to start germinating. Now, what was the other thing about the fire stick farming? It was simpler than just new plant growth, increased animal. Yeah. So we've got new plant growth, animal seed. Great, that's awesome. I'm going to come in there, and there you go. You've got feed for your family for a week. Okay. Really important thing there. And I think in some cases there might have been some as well where they the fire encouraged the rush of animals out, so you can get a bit of a feed before they come back in, and that's it. What about medicinal? Let's have a look here. This is one of the ones here. I think we've talked before about eucalyptus itself as a plant. And so we've got here tea tree oil. really common ailment. If you've ever had, it's often used in sporting injuries and stuff like that to sort of help heal a little bit there. But the tea tree oil, it works as an antiseptic. And so you apply it to some wounds and it clears it up. It reduces the rate of infection. Another really important one here, and this is the one we've talked about a few times, is the kakadu plum. Plant that has the highest amount of vitamin C of any plant or any fruit that's been discovered. And so I think at the moment there are, I think Queensland University, I think it might be QUT, Queensland University of Technology is working on using kakadu plums as a vitamin supplement. Or even as a cold and flu sort of remedy to help relieve the symptoms there. And as it says here, 50 times the vitamin C of oranges, which is probably the main one that people think about. Now, let's have a look at some more qualitative and quantitative things here. What sort of data can we get from that? Probably mainly qualitative. We've just got there, and I think that's some onion cells. And those onion cells, you know, we can say, yep, those are cells. We could turn it into quantitative data by counting up, okay? Takes a little bit of time. But in general, what we have there, when we're looking at cells, we're generally not counting the number of cells, except what might be one area of science where you want to know how many cells are there. Disease treatment involving cells. Sometimes if you're getting a biopsy of cancerous growth, you want to know how many cells are there, and that's often how cancer treatments are, the efficacy of cancer treatments is done by looking at how many cancer cells to normal cells are there. What about this one here? What phenomenon are we looking at there? Really simple. Think Isaac Newton. What's gravity? Gravity. So here is a relatively infamous one there. The guy on the right, I can't remember his name, but he was like the top physics professor at Sydney University. The guy on the left is Dr. Derek Muller, who's a Canadian-Australian physicist who now pretty much works for Discovery Channel. And so this is a thing here looking at objects falling. And of course, what sort of data is this? Would you say qualitative or quantitative? I would say just looking at there, that's qualitative because it's slowed down. You can't actually record numbers from this. But if we were looking at that in real time, we could probably get that as quantitative data. What about this here? Is that qualitative, quantitative, or both? It's both. The top part there, the tastes sour, tastes bitter, feels slippery, reacts with hydrogen, does this, does that, that is all qualitative data. The bottom part there, which is the pH scale, is all quantitative data. And so data can be both. Okay, that's an important thing to remember. What about this one here? Going back to our rock layers. Is that qualitative or quantitative? It's qualitative, yeah. Because all you're doing is relative ages. What would you have to do to rock layers to make it quantitative data? I think it's a bit of a left field question here. Yeah, sure. Yeah, use a form of absolute dating. Now, rocks like this, they usually use uranium dating, because particularly in a lot of places, there's a bit of, they use that there. You don't use carbon dating, because that's really only for living things, and it's only really accurate to about 8,000 years. Now, here, we also need to remember some definitions. And all these definitions here that we're going to go through really relate to investigations. So one of the things we've started getting into as you move into stage 6 is really focusing on the idea of methodology and how you go through it. So you've got the idea of a variable. A variable is something that changes in your investigation. In some cases, you know, that variable can change, and we'll look at those in a little bit more detail there. But you can see here, factors that can be changed, maintained, or measured. Time's a variable. Distance, any time you've done an experiment or an investigation where you've actually taken a number, you're measuring a variable. Now, of course, we have our two main important ones here, the independent variable, which is what you deliberately change. So if you are doing an investigation on gravity, you might say, oh, I want to see at what. Actually, no, if you're going to do an investigation on where you drop a ball and you see how much it bounces, you can change the height to see how much energy is lost. What you're deliberately changing in that case might be the height. Some of you might have done an SRP where you did something like on which surface will a ball bounce the highest. What you're doing there, the variable you're deliberately changing is the surface, whether it's concrete, grass, wood, flooring, carpet, whatever you want to do there. Your dependent variable is what changes. Now, the fancy one there, variable that changes in response to changes in the independent variable, essentially what we usually tell you is that the dependent variable is what you are measuring. You're measuring something. So your independent variable, you're deliberately changing. Your dependent variable is what you are measuring. Can anyone guess what the next variable is going to be? Controlled variable. It's something that you keep the same. And controlled variables are incredibly important. You need to keep the controlled variable the same to make sure that what you're measuring and that your experiment later on, your investigation, will be valid. So using that example of bouncing a ball and surfaces, if we change surfaces and then suddenly you drop the ball from double the height, you're not going to get reliable data. Your data is going to be messed up. So what you would do is, if you're doing, you say, I'll drop the ball from 1 meter in every trial. You keep everything else the same so that you can look at the relationship between the dependent and independent variable. Really important thing there is your independent and dependent variable also should be that should be what you're hypothesizing. A hypothesis should be discussing the relationship between the dependent and the independent variable, which is what we've got next here. It's also here, this is all big words here, tentative explanation. Yep. It might be in the next one. Yeah, sorry. Oh, let's go back here. Yeah, we'll come back to that. Okay, your hypothesis. It needs to be unambiguous. Now, one of the mistakes every student makes when they do their first SRP is something like, I want to see how quickly things fall. It's got to be this idea of vague and unambiguous. To what surface will return the most energy is a bit more unambiguous. And it's something that you must be able to test. If your inquiry question, and I know this is one that's popped up a few, does music change people's mood? It's ambiguous. Depends on what music you're listening to. Some people might want to listen to hardcore Nordic death metal and might feel more relaxed from that. Some people might want to listen to ambient, relaxing pan flute music from Bolivia, and other people like myself will probably get angry listening to that. It's a subjective thing. There's nothing that can actually be measured because it's a personal judgment. And personal judgments don't really fit that well into scientific questions. They can lead to a scientific question, but they're not that good there. Validity, reliability, and accuracy. These are the three concepts that we probably need to think about. Any question that you're going to be asked about an investigation. So if you get a question in a paper and it asks about assess an investigation, the things you're going to be talking about are validity, reliability, and accuracy. These pop up pretty much in every investigation. Even next year, those of you doing biophys chem, these are questions that I think popped up pretty much in the HSC last year as well. Assess an investigation. And so you're looking there at the validity. And your validity is your investigation actually answering your hypothesis? Are you measuring what you intended to? So if we're doing that sort of little investigation there about what surfaces things bounce off, and you do an investigation to see how warm the room is, it's not a valid investigation because you're not actually answering your hypothesis. Reliability. Now, this is a really important one here. Do you get similar results? Now, we probably in a class, we only do a few trials, maybe up to 5, maybe 10, depending on the nature of what we're doing. And do all those results fall into the same range? Some scientists are doing experiments, so the Large Hadron Collider, they do experiments and they get millions of bits of data from that. Are all those bits of data consistent? When you're measuring, there's a lot of remote telemetry now. So the Bureau of Meteorology has, I think, at least several hundred stations around the country taking bits of data. Now, occasionally, if you look at it, you'll see a bit of data will pop up and it's really weird. It doesn't match what's going on there. That isn't reliable. You'd probably take that out. What's the term we refer to that? Outliers, yeah. So an outlier sometimes pops in your data. Sometimes it's relevant. A lot of the time it's not. It depends on the nature of the investigation. So if you're doing a simple thing like, let's go all the way back to year 7, you do your thing where you're boiling water to see the temperature and measure maybe a phase change or something like that. You probably need a few bits of data. If you are, say, measuring rainfall or something like that, you need as much data as possible. There's no set rule, but you don't just do an experiment once and then say, this is that. If you're doing, and I'm trying to think here, if you're doing analysis of genetic data and you show that 99% of people who get this condition have this gene, then that's probably reliable, okay? There's no set rule. It used to be, way back we used to teach you, you do things at least 3 times. That's not always the case. Really depends on your investigation. And of course, accuracy. Is the measurement correct? If I got you to do an experiment trying to determine the acceleration due to gravity in the lab, and we got a value of 100 meters per second squared, that's not accurate. It might be reliable. And if it's reliable and your test is valid, that must mean there's something wrong with, say, your equipment or something like that. So one of the things there, and it's a really hard thing to do, and sometimes you got to do this, is apply common sense. Does your result, one, is it valid? Does it match your hypothesis? Is it reliable? Did you get all the data similar to each other? And another thing there, just with the reliability, should all your data be identical? No. What's the name of the concept where the data is close to each other, but it's not? It's a 2-word phrase. The second word's error. The other one. Random errors. You're going to get, in any data set, you're probably going to get random errors. Now, random errors are not errors. They're not mistakes. They're just variations in the data. You got to remember, scientists use words slightly different to other people. Yes, Miss? If you're doing like an epidemiological study or study on people, and you increase the sample size of people that you're testing each other, validity, reliability, or accuracy. If you're not using, that would be reliable. If you're increasing the sample size, it doesn't necessarily increase accuracy, because in an epidemiological study, you're actually trying to find it. I think, and depends on what you're asking them. So it's not validity. Reliability is what you're doing there. Because what you're doing is you're trying to get more of the data to make sure that whatever data sets you're looking at are not skewed one way or another. So maybe that's a good example. With
her question about how many times you need to repeat something, it's not necessarily an experiment that you might do in class. It could be a sample.
Yeah.
And so the greater the population, that makes it more reliable.
Yeah, yeah. Any science, any epidemiological medical study where you would make it more reliable by increasing the data size, but you're also making it harder to actually analyze that data. And so I think that's one of the things there that's often hard in large-scale studies, is actually getting enough data, but getting enough data, one, to be reliable, but also not make it too hard to actually assess all the data. Okay, now we're going to have a look here at a couple little things here.
If you're asked to assess an observation instead of an experiment, how would you test?
If you're asked to assess an observation, you'll probably look about what tool was used to make the observation. So you would say, in this example here, we're observing the universe. That is an example of Galileo's first telescope. If you were going to observe Jupiter, that is fine. If you're going to try and observe the Andromeda galaxy, that observation is, because it's just going to look like a smudge, that observation probably isn't valid. That's a really good question. That's not something I've really thought of before. You're probably looking there at how accurate is the tool you're using. So, very good segue to this bit here. That's image of Galileo's first telescope.
How do you comment on the accuracy of the equipment being used? We're not experts in equipment.
No, and that's probably a bit beyond what we need to do in this course. And when you're talking about accuracy, you can be talking about two things. In the way we're talking about it here is doesn't match the observed value, but you can also talk about the level of accuracy in an instrument. So most of our electronic balances go down to, I think, to the thousandth of a gram. It's the, I can't remember the term off the top of my head. But yeah, you can get more accurate by looking at smaller values or bigger values.
So wait, would observing like how accurate like the tools you use, would that also include like using the proper equipment for the measuring so you're not using?
Yeah, yeah. So no, very good point. You've got to make sure you're using the right equipment to measure that. I think there was one of the multiple choice questions, and I think it pops up in the Kahoots we can have a muck around with later on. When you're making a measurement of someone doing a 100-meter sprint, do you use a sand timer? Because that's really like probably 30-second increments. Oh, not really. Do you use an atomic clock, which measures in the millionth and billionth of a second? But is that appropriate to what you're doing? A stopwatch is more appropriate. So your idea of what's an appropriate measurement is very good as well. So if we go on there, observing the universe. We can observe the universe, and people have been doing that for probably a couple of 100,000 years, have observed the universe just by looking up at the sky. That way we know the moon there. You've got there the Druids who, well, no, it's not even the Druids, sorry. Stonehenge, ancient monoliths, basically were probably used by farmers to determine when to plant things, when to get crops out. The Stonehenge in particular in England was people used to think it was done for ceremonies. Probably wasn't originally done for that. It was probably done as a very big calendar. But it's a way of observing the universe. When a certain star is in a certain monolith, it actually gives you that there. Now, that there is a modern, and if there's any telescope nerds, you can probably tell me here. I couldn't tell you off the top of my head. I just know that's a fancier version of a telescope. It's probably a refracting telescope, which allows you to observe objects a lot closer. You also then have something like this here. I think this is the Parkes telescope. And the Parkes telescope, it uses electromagnetism to observe the universe. Telescopes like this, and also like this one here, the Hubble Space Telescope, they're great advances in technology. So observing the universe, we can observe so much more of the universe now because of increases in technology. And of course we have here, that is an infamous image called the Hubble Deep Field. And essentially that is taken from some images on Hubble. Here we go. And this allows you to look, Hubble has allowed us to look at the universe in so much more detail. Heber's question before talking about, you know, if we use Galileo's telescope to observe the Andromeda galaxy, we just see a smudge. And it looks as though YouTube isn't going to be our friend today. That's fine. Oh, there it is. And you guys in here can't hear it. I can hear it in my ear there. Don't worry about the music. But essentially, this is taken from, I think, thousands of Hubble's images. And for the first time, people were able to see that a tiny, tiny speck of the sky. Interesting thing about the universe, that basically showed that the universe, doesn't matter where you look, it's got the same stuff everywhere. And, you know, conspiracy nuts like to talk about that because there's obviously aliens because there's so much stuff out there. Now, one last little bit on this one here, digital versus analog technologies. Essentially, pretty easy. Your basic stopwatch, that is an analog. Now, the interesting thing for you guys is analog technology really isn't that big a thing anymore. You can get that sort of image on your phone when you're stopwatching, but it's just so it looks cool more than anything else. However, analog technology, there are some advantages, and we've got digital technologies there as well. Analog technologies allow you to see movement quite easily. Digital technologies give you definitive numbers. So in this case here, the analog technology, as it's spinning around, you've got to make a judgment. And so you can say, okay, if you look at the face of it, you say they've done 10.2 seconds. It's a bit harder with analog technology to give you a definitive number. But analog technologies allow you to have a continuous number. You can actually see a continuous movement in that there as well. Whereas digital technologies give you a definitive thing. They give you a definitive number. They also, in some cases there, allow you to record stuff. So on your phone, if you want to record lap times on your stopwatch, you can actually do that. Quickly here, this one little thing here, primary data. When you're doing, we're not going to go too much on this bit here, but one of the things there, when you're doing an investigation and you're doing it, you're collecting primary data. You take that primary data. Tabulation means you collect that data in a table. Now, your table of data will normally start off with your independent variable, then your dependent variable. So because your hypothesis is going from dependent to independent variable, comparing them. Then often what you are going to do is you're going to take that data and you graph it. And the idea of graphing data is so that you can actually see things like trends. We'll talk a little bit later about Ohm's law. And Ohm's law is essentially the comparison of voltage and current. And Ohm's law shows that there's a linear trend, that if you increase voltage, you increase current, and it increases at the same rate. Visual graphing, and graphing is a visual representation, allows you to do that. Other visual representations can involve diagrams where you can show a relationship. And you can then also, digital representation is usually just taking that data and showing how it changes. Probably the best example I can think of off the top of my head of a digital representation is continental drift, tectonics. A digital representation can take the idea that the plates have moved and actually animate it. And so that can actually be a powerful tool as well. And of course, finally, once we've done that, we can then make conclusions. And so what you need to do is, if you're making a conclusion, what are you answering? You're answering the inquiry question and the hypothesis. So your inquiry question is, how does this affect that? The hypothesis is saying, this independent variable is going to affect the dependent variable this way. Your conclusion is answering that. Now, we're not going to go too much in this. I'm going to skip over it because we are going to run out of time. But we did do some stuff here looking at toxins, leaching of toxins at a bush tucker. Black beans there. Now, I think I showed you this exact video earlier on this year. And essentially what they do is they run a lot of water through it. It's an observation that water running through this material was able to actually remove any toxins. You also have there the location of sources of fresh water. We've talked about it a little bit there. Common one is getting dew off leaves. We're not going to worry too much about that video right now. Okay, in module 2, now, unfortunately, COVID hit us just at the time we started doing this here. But in module 2, what we're looking at here is how can we test each of those? So I think the question I've asked you here is how could you investigate this here? How could you investigate the growth of plants? What would you have to do? Yeah, so if you have planted things, you'd measure the height. Depending on what you're going to do, you might say, I'm going to measure the effect of fertilizer on plant growth. Then you put a fertilizer in there and then you do that there. Now, one of the things here, you could also do things like reactions to calcium carbonate. I think that was one we started doing that in class. Basically, you see how that calcium carbonate reacts with different materials. The life of batteries under different conditions. This is an old classic SRP one that I don't think we like you to do much anymore. But, you know, put batteries, different types of batteries into different things and see how they work there. One of the things you've got to do, you don't have to have done this, but you might be asked to outline an investigation you could do to test one of these things. And what you've got to do, what are the 3 main things you've got to think of? VRA, validity, reliability, accuracy. What are we doing there? Okay, so you've got to think, can you do a valid experiment? Can you do a reliable experiment? Can you do an accurate experiment? And what you do is just think. You don't have to memorize all of these. You just have to be able to, under certain circumstances, be able to think about how you would do these things. Now, what does it mean here about secondary source research?
Data that's collected from other people.
Yeah. So one of the things we've started getting you guys to do is do literature reviews. So when we do an assessment task, we're getting you to do a literature review. And the purpose of the literature review is to work out what people already know. And it's a really, really important scientific process. Because you might say, I'm really interested in genetics. I want to know the genetics of why some people are tall or whatever. You think, I'm going to go do some DNA research, DNA replication. I'm going to look at the DNA of all these people. That's probably already been researched. So you need to go and check what's there. You might go through and think, well, okay, I can see that this genetic data has gone to here, but it hasn't gone on there. Really, developing an inquiry question, there's no use developing an inquiry question if someone's already answered that for you. And then from there, you can work out a hypothesis. Does the genetics of your parents affect you? And the answer is obviously yes, which is why you wouldn't do it. But once you've done your research and your background research, you can then plan your own investigation. And that last bit there, avoid unnecessary. If you are a scientist working at a big university lab and you propose something and the people who give you the money to do your research say, well, just wait. So-and-so has already done this research, you're not going to get money for research. And that's a really important thing there. It is important that sometimes researchers confirm other people's ideas, but if you're proposing to try and find something brand new and it's already been discovered, you're not going to go too well with that. You've also got here, now this one here are 4 examples of secondary source data. Now, the effect of soil, salinity, and plant growth, there's plenty of stuff out there. People know this. So if you're telling me, if I wanted to just do a research project and you said, I want to look at salinity and plant growth, research has already been done. Salinity, bad for plants. If you throw salt into a plant, it's going to die pretty quickly, unless it's a mangrove. Chemical reactions in cave formation. People already know that most of cave formations is come from usually something like calcium carbonate dissolved in water. Stalactites and stalagmites are examples of essentially calcium carbonate formations that are either coming dripping or coming up. Energy storage, that's an interesting one there, because that is probably the next big energy evolution in the way people use electricity. And water monitoring. That water monitoring data is freely available in New South Wales from Sydney Water. Basically, all the water that you guys drink out of the taps has been monitored before you get there. So if you want to do an investigation on that there, you have to think about what's already there. So it's no use you saying, I'm going to test whether my water is better than someone else's down the road. That water monitoring has already been done for you. And of course, you get that data because most of this data is freely available, particularly any data that's collected by state authorities like Sydney Water, like the Bureau of Meteorology. That's already collected there for you. Now, one of the things we moved into is this idea of patterns in nature. You've got here animal migration. Here is an example of some bird migration patterns. There are some birds that migrate from the top of the world all the way down to the bottom. And understanding these patterns is kind of important. And I know someone mentioned a while ago that, you know, maybe these patterns developed over millions of years as the continents were moving around. Essentially, most animals will breed in somewhere that's warm, and some of them then travel to somewhere that's cold. Moving to comets. This is another really important one here as well. That is a tapestry, ancient historians, that it's 1066, I think it's, do we know any big history about things like that? No, but that is a tapestry, I'm pretty sure it's from 1066. What's that comet? Why is that comet important? That is thought to be one of the earliest bits of evidence of Halley's Comet. Halley's Comet comes in close to the Earth every 76 years. And I think there's even, I think ancient Chinese documents actually document it back a little bit further. Okay. Snow crystals. One of the things there, it's a bit of a myth that every snowflake is unique. They are very unique. They form on fractal patterns, but there's no evidence that of the billions of snowflakes generated every day that they're all unique. Some will be very similar to each other, but they form off this fractal pattern that is pretty unique. Nature has a lot of these fractal patterns, and we talk about it in the Year 12 course a little bit more. And of course, you've got the periodic table of elements, which essentially is Dmitry Mendeleev, who was able to see that hydrogen, lithium, sodium, potassium, I think that's probably all he had, they all reacted the same way. He put them in the same group because they formed similar chemical reactions. And of course, we've talked about this before, the fact that what was really good about Mendeleev is that he left space for where he thought elements were going to be. And within a short period of time, people had discovered those elements and they perfectly fit into Mendeleev's thing. We also have other things there. The Aurora Australis, or the Aurora Borealis, which is in the Northern Hemisphere. In the last couple of years, I think even as far up north as Melbourne, south of Tasmania, you get the auroras pretty commonly. But in the last couple of years, I think even places like Melbourne have been able to see it's the aurora. And essentially that is just a, not a weather pattern, but it's electromagnetic particles that are coming in through the magnets of the south and north pole. You also have, and here we go, those are the auroras there, pretty lights in the sweet Nordic countries are the northern lights. And that there. You also have fractals, and fractals are patterns that are generated similar to what happens in snowflakes. They're self-repeating patterns. Fractals are also found in the way that leaves and plants form. You ever look at a leaf and a plant, the patterns of the veins on the leaf are the same as the way that the trees grow, from the trunk to the branches, then into the twigs and all that there. They follow a similar pattern. You also have unstable isotopes. We've talked about that before, the idea of half-life. And half-life, even though it's a random pattern, it follows a pattern. It's just a pattern in nature. Okay, we also have pareidolia. Pareidolia is probably my favorite term in this entire course, which essentially is that if you look at stuff, it looks like something. If you look here, you know, people see patterns in nature. You look at a PowerPoint, it looks like a face. There are plenty of things around that look like that. We also have, we should have got rid of Dr. Nick, but that's all right there. Essentially, patterns in nature are that the human brain is constantly trying to find patterns in nature. And I'll fix up that PowerPoint later on so you can look at it. But any optical illusion as well is your brain trying to make sense of the world around it. And sometimes it tricks itself into doing silly things. You also have there, we talked about this before, outliers in data. And so if you've got here, and this has probably got a couple of dozen data points and one that's outside of it. Outliers are either, it's silly things, they're either significant or insignificant. Most outliers are probably mistakes or measurements that have gone wrong, but occasionally an outlier might be something significant and it might be something for a scientist to look at. We also have here some old theories, and we've talked about these in a lot of detail, and I am going through this very quickly. Spontaneous generation. Prior to about 200 years ago, it was thought that life just came out of nowhere. Louis Pasteur did an experiment where he was able to show that a broth, which is still in a Paris museum, has been sitting there for a couple of hundred years and nothing has ever come out of it. You leave that same broth overnight just sitting there in a bowl, you'll have flies coming out of it the next morning. You also have germ theory, which the main story we talk about here is John Snow was looking at cholera in London, and he was able to work out, well, no, there's something there. There's something that causes disease. Henry Becquerel, Marie Curie worked out that radiation, things spontaneously decay and you can get energy out of it. Becquerel, he basically was the first person to do an X-ray. He discovered that photographic film was interacted with that there. Phlogiston was a pre-oxygen theory, and the idea was that substances had phlogiston in them. Phlogiston burnt. At the time, no one really knew about oxygen. So it's a lot of these theories come about because there's a misunderstanding about the processes. We don't understand everything. And sorry, human influences on atmospheric pollution. We are mainly talking about climate change, but there's plenty of other things there as well. Okay. And I'm going to go through this because I've already talked about that there. That is the first X-ray. That is a bit of, I think it was plutonium might have been sitting on a photographic plate. There's Marie Curie and phlogiston. You know, I'm just going to quickly, go through this. And of course, we do have the idea of pollution caused by a lot of things. And that is, I believe, Shanghai. Okay. One of the things we didn't really get much of a chance to do, we talked about it a few times here. If you were asked to do one of these things here, how would you undertake that investigation? You might be asked a question on, here is the premise, how would you investigate this? Now remember, we always have to, any time that you're going to do an investigation, talk about validity, reliability, accuracy. How are you going to maintain those things? Now, that is module 1 and 2 in a very, very short nutshell. I'm going to finish that now, and you guys can have a little bit of a break.